this formula, now we'll substitute the value of n as 1. So you'll get I, which is equal to integral x0 to x1 y dx, which is nothing but n into 1 h into 1, so h into y0 plus delta y0 upon 2, and the rest of the term, that is in this delta square y0, if you observe, then delta square y0 is nothing but delta into delta y0, which is y1 minus y0, and which will be equal to again delta y1 minus delta y0, which will give you y2 minus y1 minus y1 plus y0. So this will be equal to y2 minus 2y1 plus y0. If you observe, then now we had a graph where the integration was over x0 to xn, and we have taken one sub part of it, that is x0 to x1. So if you have this function, then we will just look into consideration about this part. So while calculating the integration, we won't be considering any value of y2. y2 is nothing but value of yx2, which is not a part of this integration. So we can avoid the rest of the part except this. So we have to consider y0 plus n upon 2 delta y0. So this is a required answer. So after this, you will get h into y0 plus delta y0 is nothing but y1 minus y0 upon 2, which is equal to h upon 2 y0 plus y1. Okay. Similarly, concluding in this manner, like if this is the case, it won't be I actually, because I is the entire integration. We are taking just part of it. So we'll just consider one integration from x0 to x1. So similarly, if you consider another integration over the next part, that is from x1 to x2. So if this is x2, then if you want to calculate the area under this part, so we will get integration x1 to x2 y dx, which is equal to h upon 2. Now instead, when we were considering x0 to x1, we had the summation of their respective values of the function, that is y0 plus y1. So here we'll get y1 plus y2. So this is the second equation. This was the first one. So considering in this manner about the different sub-intervals of that interval, if we consider the nth interval, that is from xn minus 1 to xn of y dx, it will be equal to h upon 2 yn minus 1 plus yn, and that is the last, or if we consider, then it's the third equation. Okay. So if we want to calculate the integration over the entire interval, we can add the integration of the respective subintervals. So instead of calculating for whole, we can have I equals to integral from the first initial, that is x0, to the last xn point y dx is nothing but the addition of all the integrals of the subintervals. So that is equal to h upon 2, we can take it as common. What we are left is with y0 plus 2 times y1 plus y2 plus up to so on yn minus 1 plus yn, and this formula is known as trapezoidal rule. Okay, so if you are asked to find the value of integration by trapezoidal rule, you have to make use of this formula. So now to find the error of this rule, you have to use Taylor series expansion. So again, if you want to consider integral x0 to x1 y dx. So it is equal to x0 to x1. Instead of y, we have to make use of Taylor series expansion around x equals to x0. So the value of Taylor series expansion is nothing but it is y0 plus x minus x0 into y0 dash plus x minus x0 square upon 2 factorial into y0 double dash plus up to so on dx. So solving this with respect to x, we get y0 into h plus h square upon 2 y0 dash plus h cube upon 6 y0 double dash plus up to so on. So this is the actual integration. So in RHS we have h upon 2 into y0 plus y1, which is equal to h upon 2 into y0 plus, now y1 is nothing but y of x1, and this y of x1 can be written as y0 plus y of x0 plus h. So now this will be equal to h upon 2 into y0 plus y0 plus h into y0 dash plus h square upon 2 into y0 double dash plus h cube upon 6 into y0 triple dash up to so on. So this will be nothing but h upon 2. So this y0 and again this y0, so 2 y0, so this is just h y0 plus h square by 2 y0 dash plus h cube upon 4 y0 double dash plus up to so on. So now error is nothing but LHS minus RHS. So this is equal to integral x0 to x1 y dx minus h upon 2 y0 minus plus y1. So after subtracting all the both the equation LHS and RHS, the final answer is nothing but minus h cube upon 12 into y0 double dash plus up to so on. So this is the interval in the first sub part, that is sub interval from x0 to x1, because we have calculated for just h upon 2 y0 plus y1. So this is for the sub interval from x0 to x1. So similarly you'll get the error for it. So if we consider the error for remaining sub interval, then the final error E for the entire interval from x0 to x1 xn will be given by minus h cube upon 12 common into y0 double dash plus y1 double dash plus up to so on plus yn minus 1 double dash. So this is the total error E in the trapezoidal rule. So now our next point is Simpson 1/3 rule. So Simpson's 1/3 rule. So for this, as in the earlier part for trapezoidal rule, we had substituted value of n as 1 in the equation y in I equals to integral y dx, which is equal to n into h something something, right? So in this, if n equals to 1, then we'll get the trapezoidal rule, and if n equals to 2, and then we'll get the Simpson's 1/3 rule. So to calculate this, we'll have x0 to x2 y dx equals to, after substituting n equals to 2 in RHS, we'll get 2 into h into y0 plus delta y0 plus 1/6 delta square yn, delta square y0, sorry. So solving this, we will finally get the answer as let's solve this. So it's 2h into y naught as it is. Delta y naught is nothing but y1 minus y naught plus 1 upon 6. As we have seen before, delta square y naught is nothing but y2 minus 2y1 plus y naught. So it is 2h into, so this is y2 upon, so y naught will get cancelled. So you'll be left with y2 upon 6, then plus y1 minus 2 y1 upon 6 plus 1 upon 6 into y0. So this will give you 2 upon 6 into y2 plus, so this is 6y1 minus 2y1, so it will be direct, we can directly write 4y1 plus y0, which is equal to h upon 3, sorry, h is missing over here, so h upon 3 y2 plus 4y1 plus y0. So this is our first equation for one subinterval, that is for, if this is your a and b, then we'll divide it from x0 to x2. We won't consider here x1. So we will divide the subinterval into length of 2h each. So similarly, if you consider the next subinterval, then it will be, second interval will be x2 to x4 y dx equals to h upon 3 y2 plus 4y3 plus y4. So that's a second equation. So going in this manner, we'll get integral xn minus 2 to xn y dx equals to h upon 3 yn minus 2 plus 4 yn minus 1 plus yn. This is the third equation. So now if we combine again, then the entire integral, that is integration over the interval x0 to xn, is given by integral x0 to xn y dx equals to h upon 3 is taken outside because it's constant, common. So y0 plus 4 into y1 plus y2 plus, sorry, y1 plus y3 plus up to so on plus yn minus 1 plus 2 into y2 plus y4 plus up to so on plus yn minus 2 plus yn. So this is known as Simpson's 1/3 rule. Okay, so we have to make use of this formula for solving the sums. We'll see further how we can solve it. So again, to find error, we need to use Taylor's formula to expand y around x equals to x0. So again, if you consider the LHS, which is nothing but x0 to xn, x0 to x2, for that subinterval, it is y dx, which is nothing but x0 to x2 y0 plus x minus x0 into y0 dash plus x minus x0 square upon 2 y0 double dash plus up to so on x minus x0 cube y0 triple dash upon 6 plus up to so on dx. Integrating this, so we'll get directly y0 into 2h plus 2h square upon 2 y0 dash plus 2h cube upon 6 y0 double dash plus 2h raised to 4 upon 24 y0 triple dash plus 2h raised to 5 upon 120 y0 fourth dash. So this will give you 2h y naught plus 2h square y naught dash plus 4 upon 3 h cube y naught double dash plus 2 upon 3 h raised to 4 y naught triple dash plus up to so on. Now, so that was our LHS. Now we'll consider our RHS. So RHS is nothing but h upon 3 y naught plus 4y1 plus y2. So this will give you h upon 3 as it is, y naught plus 4 y1 is nothing but y of x naught plus h. Okay, so this is a x naught plus h is x1, so y of x1 is y1, so plus y of y2 is nothing but y of x naught plus 2h. Okay, this x naught plus 2 is just because x2 is nothing but x1 plus h, and x1 is nothing but x naught plus h, and this h is as it is, so it is x naught plus 2h. So y of y2 is nothing but y of x naught plus 2h. Now we'll continue this. So we'll get h upon 3 as it is, y naught plus 4 into, so value of y of x naught plus h is nothing but y naught plus h into y naught dash plus h square upon 2 factorial plus h cube y naught triple dash upon 6 plus h raised to 4 upon 24 y naught raised to 10 plus up to so on. This is the value of y of x naught plus h, which we had seen in numeric integration, numerical something part previously. And similarly, value of y of x naught plus 2h is nothing but y naught plus 2h y naught dash plus 2h square y naught double dash plus 4 upon 3 h cube y naught triple dash plus 2 upon 3 h raised to 4 y naught raised to 10 plus up to so on. So solving this, you will get 2h y naught plus 2h square y naught dash plus 4 upon 3 h cube y naught double dash plus 2 upon 3 h raised to 4 y naught triple dash plus 5 upon 18 h raised to 5 y naught raised to 10 up to so on. Y naught, fourth derivative of y naught. Fourth derivative of y naught. So now error is nothing but the difference between LHS and RHS. So LHS minus RHS will get it as integration of x naught to x2 y dx minus h upon 3 y naught plus 4y1 plus y2 which is nothing but 4 upon 15 minus 5 upon 18 h raised to 5 y naught raised to 4, that is fourth derivative of y naught. So this will give you minus 1 upon 90 h raised to 5 fourth derivative of y naught. Now this is an error in the interval x0 to x2. Similarly, we have to find the error between the consecutive intervals, that is x2, x4, xn minus 2, xn. So the total error is nothing but it is e, which is given as minus 1 upon 90 will be common. Similarly, h raised to 5 will be considered outside. So y naught raised to 4, that is fourth derivative of y naught plus y2 raised to 4, that is fourth derivative of y2 plus fourth derivative of y4 to so on. fourth derivative of yn minus 2. Now if third derivative of y attains the maximum value at some point, say epsilon, which belongs to the interval a comma b, then if we take n by 2 integrals of the equation, then we'll get that error e is equal to minus n upon 2, so n by 2 into this 90 into h raised to 5 into y raised to 4th of that point epsilon. So finally e will be nothing but it is h minus e upon 180 h raised to 4 y4 of epsilon. So now we'll see one example. So now we will see few examples. The first is you have to evaluate for I, that is integration of 1 upon 1 plus x dx, which goes from 0 to 1, and we have to solve this example by both trapezoidal and Simpson's rule. So here we have h equals to 0.5, 0.25 and 0.125 respectively. Okay, so as this is the value of y, so we can write it as y equals to 1 upon 1 plus x. So first, for taking h equals to 0.5, we'll have values for x and y. So first x naught, which starts from the integral limits, so x naught which is equal to 0.0, so for that the value of y will be 1 upon 1 plus 0, that is 1, so it is 1.0000. It's best to take four numbers after the decimal point. Similarly, x1 will be nothing but for h equals to 0.5, the next point will be 0.5. So calculating value of y, for this you will get 0.6667. Substituting value of x as 0.5 in this equation, we'll get this value of y. So this will be y0, this will be y1. Similarly, x2 will be nothing but the next point is 1, and that's the extreme point for the limit. So that's the end point. So for x2 equals to 1, we have value of y as 0.5. So this is the value of y2. Now we have to solve by both trapezoidal and Simpson's rule. So first, by trapezoidal rule, we have the formula as x0 to x1 integral x0 to x1 dx, x0 to x2 dx, which is equal to h upon 2 y0 plus 2y1 plus y2. So we have x0 to x2 as 0 to 1, y dx equals to h's are 0.5 upon 2 into 1 plus 2 into 0.6667 in plus y2 is nothing but 0.5. So this will give you 0.70835. That's the answer. Okay, so we had calculated the values for y0, y1, y2 using this formula. So we need to just substitute this here and we'll get the value of that integration. Now next is by Simpson's rule. So for Simpson's rule, we have the formula integral x0 to x2 y dx equals to h upon 3 y0 plus 4y1 plus y2. So this will be nothing but 0.5 upon 3, y0 is 1 plus 4 into y1 is 0.6667 plus y2 is nothing but 0.5. So solving this, you'll get value of this integration as 0.6945. So this is your integration value I by Simpson's rule. This was by trapezoidal rule. Similarly, you need to solve for h equals to 0.25. So for this, so let us consider h equals to 0.25. So now we'll calculate the values for x and y respectively. So our first point, which is x0, it will be our initial point, so it is 0.000, and similarly your y0 point will be nothing but it is 1.0000. So this is y0. So now x1 will be nothing but addition of h to this point x0, so you'll get 0.25. so respective value of y, that is y1, is 0.8000. next value is x2. so adding this h to this x1, you'll get 0.50. respective value of y is 0.6667, that is our y2. x3 is nothing but 0.75, and respective value of y is 0.5714, that's our y3. x4 is 1, that's our last point of integration, that is limits, so it is 1, so y value is 0.5, so that is our y4. So now for this, our trapezoidal rule will be I, which is equal to integration x0 to x4 y dx equals to integral 0 to 1 y dx, which is equal to h upon 2 y0 plus 2 into y1 plus y2 plus y3 plus y4. So this is nothing but 0.25 upon 2 into 1 plus 2 into 0.8 plus 0.6667 plus 0.5714 plus 0.5, which is equal to 0.6970. So this is the integration value. Similarly, by Simpson's rule, we have the formula as x0 to x4 y dx is equal to h upon 3 y0 plus 4y1 plus 2y2 plus 4y3 plus y4. So this is nothing but 0.25, that's value of h upon 3 into y0 is nothing but 1, so 1 plus 4 into y1 is 0.8 plus 2y2 is nothing but 0.5714 plus 2 into 0.6667 plus 0.5. So this is nothing but 0.69325. So this is the value of integration by Simpson's rule. So now for h equals to 0.125, here the steps will increase because the difference between the two